Good afternoon, everybody. Welcome to today's webinar from PSDI. So today we have another webinar in the PSDI Pathfinders series. So the Pathfinders are some of our initial exploratory work that is looking to explore some of the requirements that would be needed for core services to support physical sciences, and also building some initial services to focus on potentially specific domains or cross-domain topics. So today we're joined by Sathya Sai Sitharaman from STFC Harwell, and he is going to be presenting about one of our Pathfinders, Pathfinder 6. So this is a Magres database for the solid-state nuclear magnetic resonance community. And now, without any further introduction, I'm going to pass you over to Sathya for the presentation today.
Thank you, Nikki. Hi, everyone. I'm Sathya, and today I'm going to talk to you about the Magres database for solid-state NMR community. And thank you to PSDI for providing this webinar platform so that we can use this as a nice snapshot in time to document our current status, where we stand, and revisit this in the future when we have made progress. And a little bit about me before I go into the main presentation. I'm a senior computational scientist at STFC, working in the scientific computation department for almost a year now. And before my time at STFC, I trained as a physicist, and I worked for 4 years as a research scientist in consumer electronics and automotive industries. A main aspect of my role in these industry positions was to develop computational tools for a wide range of engineering applications, such as predictive analysis, experiment automation, data collection, processing, and analysis, which are all quite relevant to the role that I'm doing today at STFC. And I am the Pathfinder lead on the Magres database project for CCP-NC and PSDI, which is the main subject of today's talk. A little bit about what you can expect from today's talk. I'd like to begin by talking about the CCP-NC community, who are the community of users who generate the data that resides in the Magres database. And I'll talk a bit about the background of Magres, what it is. I'll proceed to talk about the current state of our Magres database, our current technology stack, and the efforts that we have put in to make the database compliant with FAIR specifications, and the challenges that were presented to us as we move along. And given these challenges that keep us from achieving FAIR compliance satisfactorily, I would then talk about what would a better, ideal, improved stack look like for a better version 2 of this Magres database. And I'll conclude the talk by talking about what are the intended outcomes and when we aim to achieve these outcomes. The community of CCP-NC comprises of experimental NMR researchers from multiple UK universities and pharmaceutical R&D teams from industry. I have not had the space to list all of our academic members here, but there are also universities like Cardiff, University of East Anglia, and University College London and Lancaster, who are also part of our academic members in CCP-NC. The role of STFC is to make available research software engineers and computational scientists who provide the core computational support to CCP-NC by developing their computational NMR software, Python libraries, and NMR visualization tools. The academics that I mentioned in the previous slide, who represent the CCP-NC community, are a good mix of both organic and inorganic materials researchers with strong ties to the pharmaceuticals industry. The CCP-NC aims to promote the usage of computational tools by this predominantly experimental community, which is facilitated by STFC, as I mentioned. And to talk about NMR crystallography itself, it represents the combined use of experimental NMR techniques and computation to provide new insight into the structure, disorder, and dynamics of the materials in solid state with atomic resolution. And CCP-NC strives to be the source of best practice guidance on computational NMR crystallography. We can say that NMR crystallography is a relatively new field, with especially an accelerated research activity within the last 2 decades after a crucial development in the ab initio computation method, when the method that's abbreviated as the GIPA method was proposed in 2001. Currently, there are more than 20 density functional theory codes that adopt this GIPA method and have the capability to calculate solid-state NMR parameters. And the NMR calculations were added into the DFT code CASTEP through direct efforts of a few CCP-NC members who continue to lead CASTEP development and the documentation. To go into talking about what Magres is, the official documentation for the need for the Magres files and how the Magres file is structured and why we need it are all available in this document. But I would also talk a little bit about Magres here. Since I mentioned that there are 20 plus DFT codes that have the capability to do NMR calculations currently, they tend to output the calculated parameters in their own respective file formats. And the reason for the formation of the Magres file format by CCP-NC is to standardize the density functional theory NMR data outputs. So they created the Magres format in 2014. Typically, I'll talk a bit more about the constituents of the Magres file, but at a top level, it contains the crystal structure information and the calculated parameter data, plus any metadata that come with the calculations. The Magres view is the CCP-NC community's crystal structure viewing tool that is compatible with to work with Magres files as well, that lets you visualize not just the unit cell of the crystal structure, but also visualize on a relative scale the calculated NMR parameters. And we have had 2 density functional theory codes, CASTEP and Quantum Espresso, add support for the Magres file format outputs to output the NMR parameters directly in the Magres file format. And the Python library Atomic Simulation Environment, ASE, also has a reader writer that's compatible with the Magres file format. To do an in-depth analysis of the Magres file, to mention briefly, it has 3 main blocks, which is the atoms block, which contains information about the atomic coordinates, symmetry, and optionally also lattice information for reconstructing the structural information. And there is the main Magres block, which contains the calculated magnetic resonance parameters. At the moment, it tends to be magnetic shielding and electric field gradient. And this representation is chosen to represent these parameters, which tend to be 3x3 tensors in an easier format in a text file. And currently, work is underway to extend support for Magres to include paramagnetic material properties as well. At the moment, it supports diamagnetic material properties to be calculated and included in Magres. And finally, there is the calculation block, which includes the important calculation metadata from the DFT code. Details like the code name, the version of the code, date of calculation, and further input parameters. At this point, if I can take a quick pause and actually show you what a Magres file looks like from our database. This is a Magres file. And as you can see at the top, you can see a calculation block that contains relevant metadata about the calculation code CASTEP, the version, the date of calculation, even the platform on which the calculation was performed, and the initial input parameters that were used for this calculation. The atoms block expresses coordinates in angstroms, the lattice information about where the unit cell is centered, and it lists the individual atoms in order that form the molecule, and the respective coordinates of each of these atoms with respect to the central lattice coordinates, which can be used to reconstruct the crystal structure. And finally, the Magres block that contains data with the prefix of MS indicating magnetic shielding. And down the file, there is EFG indicating the electric field gradient. The atoms here are listed in the same order as they were listed for the crystal structure. And the 3x3 tensor is represented as a single line of 9 values per atom, which can be parsed. It's pretty simple to write a parser for this Magres data type. So to get back into the presentation, you notice that these blocks are all individual of each other. It doesn't matter in what order they are output by the codes in the Magres file. As long as these tags are readable, a parser can easily extract the relevant information from these data blocks. These blocks are not overlapped or nested within each other. They are independent. And the intention of this structure within the Magres file is to maintain a lightweight file structure while removing the need to individually store the input and output files from the computation separately. The Magres file is intended to be self-sufficient, containing all the metadata information and the final output information that were output. Proceeding to talk about our database that houses the Magres files. As you can see, this is a fairly simple stack, which was the actual intention with the database, as this version 1 was developed first in 2019 to be a prototype to provide the data services for the community. At the bottom at the bottom of the stack is the database engine run by MongoDB, and Flask is a lightweight Python library that handles the backend operations, and it also handles the representational state transfer between the front end and the backend queries. We provide user authentication on our database using ORCID, which is a fairly elegant system, and it has suited the community's needs so far. And sitting right at the front is AngularJS, the JavaScript framework that was used to build the front end for the database website. I have to mention that this is a pretty old framework. And this, as I mentioned, the database has been operational from 2019 at least, and this framework is a bit older than that, and there have been several iterations of this library since then. But in the project, there have been movement by software developers have moved projects or left the organization, and hence the community has not had a chance to upgrade the front-end version when the time was right. So this is a bit outdated and it is in need of an update. So, and as you can see, there is no public API that's made available by the database to query the database using Python codes or from a command line interface for bulk data extraction directly. And if you are interested in visiting the database website yourself to have a play around, that is the URL for you. So before I go into talk about fair compliance, we all know that the fair compliance is composed of the findable aspect of the data, accessibility, interoperability, and reusability of the data. I'll address how our database evaluates against each of these metrics as I proceed through the presentation, but I think this is a good place to pause and show you another demo directly of our database so that I can come back to talk about some of these non-searchable fields that are present in the records but are still useful. And to give you an overview, there are close to 5,800 Magres entries in our database currently, and they are a mix of both published and unpublished data, each with their own unique IDs. And we welcome unpublished data sets, and the users have the option of coming back to create versions when they have a published data set, they can create a newer version of the data set, and we retain both the old and new version by maintaining the modification date of each of those versions and the unique files that were created for those versions. So if I take a step back, and as you can see, this is our database. And as you come to the homepage, you can very clearly see that this is a prototype database. There is not much to go on with the homepage, but this is designed purely for functionality. And I have not logged in to the website yet, but it lets you search already. And I would maybe search for a specific record by an internal reference ID. If you know the internal database reference, if someone has provided you with the reference for a record, you can search for it right away. For example, this is one way of finding a record. And if you take a look at the record, I first want to talk about data that are present and on the front end, but these are data by which you cannot search the records. That is the ORCID identification details of the author and the author who uploaded the data set, and the ORCID link directly provides a link to the profile of the author where you can find their affiliations and their other work and attributions. This particular example has only one version of a record created. So, but you can see that it includes the version number and the date and time of last modification, which you can choose to see the individual versions. But by default, the database displays the latest version, assuming that that is the most correct version uploaded by the user. And there is additional notes, which is additional text-based metadata by the user as well. And that is the licensing information and external database references and DOIs, which I'll go back to talk about in a minute. So coming back to the presentation, if I go back, I can show that there are calculation metadetails, but the calculation metadetails here are insufficient for Quantum Espresso output files. So if I go back to show you another record that was not calculated by Quantum Espresso, maybe I'll talk a bit later about why, what's missing. But to show you another record, maybe this is a much more informative file in terms of metadata that's output by CASTEP. As you can see, this block of data is quite similar to the block that you would find in the Magres file. This is extracted directly and stored in the backend. But at the moment, you cannot search for records by code details. So data version and modification date and file IDs are used primarily for backend purposes. But on the front end, you can choose different versions to extract the records associated with those versions. But you cannot straight away search for records by those versions on the search interface. And of course, there is the free text metadata that a user is free to enter at the time of uploading the data, which the upload interface I'll show you in a minute. But it doesn't make sense for a user to search for a free text metadata to find a record. And of course, there are user details that are held on record that will be displayed along with the records when you search for records, but you cannot search for a particular uploader. And the community didn't see the need for doing such a search. The calculation metadata, it is highly desirable to make the calculation metadata details like the code name, the particular DFT code and code version and such as searchable fields. But the challenge presented here is that at the moment, this data block that's extracted from Magres is directly stored as a string, only to be displayed on the front end. And the database schema at the moment does not permit individual data fields for this. It's not present. So it presents a challenge for making this metadata directly searchable on the front end. And another set of identifiers that we store in the backend or what you may call molecular fragments. The Magres parser that works in the backend of our database. It works with the crystal structure information and the distance information between atoms to determine which atoms are bonded to each other and to determine which atoms form groups or clusters within a unit cell, because you can have collections of multiple molecules within a single unit cell that make up an entire material. They don't all have to be bonded to form one single molecule. This is a powerful piece of information that we hold that can enable a user to do what you may call a fragmented search, or for example, some organic chemistry users may want to search for materials by functional groups, and such a feature is made possible by holding this information. But at the moment, we have not made this searchable, because I think in thinking about how one may search for these molecular fragments on the front end, I think to search for a substructure or superstructure searches, many open source crystal structure drawing tools exist, and some open source databases are also powered by these tools, where a user can draw the molecular structure using given tools, and they can create a fragment and say that this is a functional group and I want to find all the records that have this substructure in them, or there is also the superstructure search. And as I mentioned, given the current state of our front-end framework, we have now decided that it's maybe a bit redundant to include more tools on the front end that will let users to perform these searches. And this is temporarily been put off as a development for the future. And another metadata that's not searchable but still used in the backend for powerful searches is tokenization of chemical names. If I go back to the search interface, one could choose to search by chemical name. As you can see that this is a pretty free text search, and the user has the option to simply say, I want to find all records that contain the word methyl, but I don't want the word methyl to simply be existing on its own. Any methyl phenyl is also permissible in the records, for example. And in the returned results, as you can see records that contain the word methyl and also compounded word methyl phenyl. So if you open this record, what our parser does when uploading a Magres file is, it treats these chemical name. This is an IUPAC convention chemical name that's entered by the user. But it takes up the name and it looks for strings that are not just alphanumeric combinations or single characters, and it takes these letters and store them as individual tokens. So it powers these wildcard searches where a user may mention in double quotes that I want to look for this string or other parts that are attached to it. So it performs a substructure search within these tokens as well, other than just in the name as a whole. So I can move on to talk about the ORCID authentication. The ORCID authentication powers our system. As you can see, you can search for records really without logging in. For example, if you pull all the records, okay, I know what I did. So you can search for all these records and you can simply download the Magres file or the associated metadata that's in the backend all as a JSON format. You don't have to log in, but you can see that you cannot upload anything to our database yet. So which needs to come in with a login authentication. It's a simple two-step authentication process. You go to an ORCID page, which lets you log in, and it passes the ORCID user information back to our database, which are exchanged with the backend for some tokens, and a successful login message is displayed with my ORCID ID, and it just shows my ORCID ID, and I can just click it to go to my ORCID profile as well. And as you can see, two other features are made available once you log in. You can upload Magres files, either as a single Magres file, for a standalone calculation that you have done, or if you have a collective data set that you have generated, and maybe it's a published data set and you want to upload it as a collection, you can upload it as one of these archive formats with all the Magres files. But at the moment, I think this involves a little bit more work on the uploader's side, because we require them to fill out a CSV file, which is a spreadsheet that contains all the individual file names, and for them to fill each of these individual metadata fields that are normally asked in the form, so that each file is associated with the right metadata when parsing and putting in the in the backend. And this is a feature that needs improvement, and it's currently in our to-do list to improve the user experience when uploading. But as you can say, the name and license are definitely mandatory fields for users when they upload the data. And when they upload name, the name is permissible as free search. And as such, we recommend that users can either use common names or descriptive names that describe the chemical form of a molecule as well, or the IUPAC names, as you have seen in some of the examples that I showed. We make available 3 licenses, of which PDDL and CC BY are the most used, and ODC normally requires usage in combination with another license. So users tend to either use PDDL or CC. PDDL is a lot more open than CC BY. PDDL essentially puts your data in the public domain, and it doesn't enforce data attribution. And if you think that, like, if you say that I generated a large data set, but I don't really care about attribution for it, maybe I just generated it for training a machine learning model, I'm going to train it, I'm going to put it in the database, and I'm okay with anyone using this for training their models as well. One may go with PDDL. And CC BY is the Creative Commons data license that enforces that whoever uses the data set must give attribution to the data owner. And if one clarification to make here is that in the search interface, we simply mention DOI. DOI is quite a broad term for an identifier for any digital object that you may find online. But the DOI that we are expecting here is a publication DOI that a user may or may not enter with their records at the time of uploading, which makes the data later searchable via publication details. And if the same structured information has other parts of information that are held in another materials database, they have the option of either choosing the preset options of CSD, ICSD, COD, or choosing the other option and then mentioning a custom name of the database and the reference code for the database at the time of uploading. Or at the moment, if they don't have information, they can just choose not applicable. And nodes is the free text metadata nodes that a user can enter, something similar to this at the time of uploading, so that any person may find additional information useful. These structural descriptors are relevant to the face of the material. Sometimes there are structural variants. According to the different methods, you make many structural variants of a material, and you want to make end user aware that this is a form number 1 or 3rd form or 4th form of the material, or any other descriptive information that you want to include about the material, about the data. Sometimes users also add notes saying that for more details, refer to this DOI, and link them with the DOI saying that there is a method A that's described in this publication that's mentioned in the DOI, and this structural variant was modified according to that information. And a user can do that. And normally, if you upload records, you can then go to the Your File section and you'll find your uploads there. About the searchable fields, I did mention the DOI search feature and all these other features that we make available that are searchable. I'll go back in a minute, but I just want to quickly highlight the categories that we have. Like, you of course have the core data categories that include the calculated parameter by which a user may want to search for records. And of course, the material identifiers. How would you identify materials? Either using the chemical's name or the structural descriptor, which is included in chemical form, or the unit cell formula or the molecular formula, IUPAC formula of the materials. That's if it's included with the records, and licensing information for reasons that I mentioned before, depending on what purposes that you are using the records for. And the immutable ID is the Magres Database reference code that's developed by the CCP-NC community for the database, with the intention of being the equivalent of the reference code that's provided by databases like CSD and ICSD. This is used for internal database reference, and the intention is that these can also be used for attributions in publications if you want to include them in your papers. And there is the external database reference, as I mentioned, which can refer to an external publication, redirects there, or a reference code or a database name. And one of the recent developments that we have done is to include a Boolean search feature that adds a little bit more power to data filtering for more efficient searching, which I'll show in a minute. So as I said, you may come to the search and you can say that, okay, I'm looking for, of course, for the DOI, you can enter the entire DOI. This is a case insensitive search. But you can also do a partial string search saying, I know that the DOI prefix for Science Direct is this, and I want to look for all the records that begin with the DOI. And you may then combine this with another condition saying, okay, for this search, I want to filter these results even further. I am more interested in records that are published in the journal called Solid State NMR. I remember that it has the string SS NMR in the end, but I don't remember the before and after of it. So you can simply include wildcards on either side to say that this is in the middle of the string, and you can filter this result further. And if you look at one of the records, you would see the final DOI that can redirect you to the actual publication. Coming back, if you decide that, okay, I want Science Direct and Elsevier publications, but probably I want all the other records that are not published in this journal, you can simply flick the not switch to say that, okay, I want to exclude this result, and then you will be given the other subset of information, which is which adds a little bit more flexibility to search for users to perform efficient searches. If I have to give some more examples about the other functionalities, of course, the core parameters by which we expect users will search are through magnetic shielding and electric field gradient. And essentially, the 3x3 tensors per atom for the materials from the Magres file are extracted, and there is a diagonalization process that's performed on the 3x3 to store it as a 3x1 value in the backend to calculate the parameters. And if you are a more advanced user, you can then specify and say that I want to look for all the records that have the hydrogen atom and maybe the magnetic shielding value in the range 10 to 200. I personally, as a non-expert in density functional theory and solid state NMR, I wouldn't know how to set these ranges. But I think if you are a more advanced user of the community, we have given the functionality for someone to do such a search. And this is such a big data set. And I want to filter the data set even further. I'm not sure I can find the results that I want in here. Maybe I look at the list and I want to look for more of records on tolfenamic acid. So I add the results. I add a search condition. I choose chemical name and I just say, I want tolfenamic to be present in the string, but anything that follows tolfenamic is okay. Please filter the results for me. And from about 4,500 results, now we have just 68, which is a good filtering. And I may want to say that, okay, I want to say or do any of these records have association with the Cambridge structural database? I want to find all the records, and you don't have to mention the particular reference code in the first instance. You can just say, I want all the files that have CSD reference to it. There was just one file which didn't. But if you want to filter this further, you can say, okay, I also want to find records that have unique reference code from CSD that's entered by the user. And okay, I filtered the results down too much. This may present one variant of the structure, but I also want to look at other structural variants of this material if the user has entered that information when uploading. And I can simply say, okay, also show me some other structural variants, and you will end up with 13 results. You can then say, okay, I want to download these records, but before then, I want to make sure that there are no restrictions on the files. And fortunately, I mean, for these 13 files, there were no restriction when I searched that or any of those have CC BY attribution. You can just say that I don't want to include CC BY, and you would end up with the results back as you had them before. So yeah, that's a short demonstration of currently what you can do with the database. And we are still in the findability part of the presentation. I need to keep moving. We talked about the freedom for the user to perform free text-based searches, but the primary problem associated with it is that there is too much freedom, and there is less room for standardizing material searches by using standard chemical identification processes and identifiers such as INCHI and SMILES formats. And if it is too free text, this prevents us from doing such a search. And another area that might be a bit of a problem is, though the immutable ID is developed with the intention of being treated as the unique reference code of the database, in case there are journals that prefer that there are standard DOIs that are minted when generating these records, which are then used in publications, then this may be less favorably looked upon. So a DOI minting process inclusion along with generation of immutable ID is desirable, but it's not available in the current iteration of our database or the features that we provide. And lastly, for enhanced user experience and for our community, for the CCP-NC community, and what they can get out of the Magres data instead of just searching for files based on numbers, it would be nice to integrate the Magres view and other NMR data visualization tools on the front end, as I showed before. But given the current state of the front end, this also goes to a great to have list for a future development. To summarize the findability aspect, I spoke about the free text features, the challenges associated with having non-searchable fields which are still usable, and fields that are searchable but where some improvements could be made. And I already mentioned that we lack a public search API for more homogenized data sets to download data sets in bulk for machine learning purposes. And the data, as you could see from the stack that we have, is also not indexed. We don't have an indexing layer to perform a specialized search. The search is performed at runtime. As you may see that when there are like 4,500 results fetched from the backend at the same time, the search is a bit slow because the query is constructed and processed at runtime. This is a bit slow. And also by best FAIR data standards, the data indexing is not done. But the prototype does its purpose. It is a database that provides a data service, and it lets the user discover the data by certain main searchable fields. Moving on to the accessibility part of it, the lack of public search API was mentioned, but the intention in the current version of the database is for users to anyway go to the front end and access the data from the front end and download them without login. So we provide open access, but where necessary, we enforce ORCID authentication for file deposition as well. And this is made clear on the front end of the database. And I talked about the licenses and what each of them mean. And in terms of the bulk download, I think the community has a preference. This is a feature in development, but I think we don't want all data sets to be permissible for bulk download all the time. But if it's enforced if the files are PDDL permissible and you just want to download a huge data set for machine learning training, for example, you can just download them. But this feature is not available yet. It's in development. For more restrictive licenses like CC-BY, I think we would like to hold back the feature of letting download one at a time. In terms of accessibility, one thing to talk about is that a problem with deposition is that researchers may not always be encouraged to go to a database to deposit their files whenever they generate data and when they are planning to publish it. They may simply use their own institutions' repositories, for example, most of which may be open source, but there may be some repositories that require member access. And therefore, attributing just these repositories and the datasets in a publication may present a problem where the dataset is locked away and not accessible to some people. But another thing to mention is that if the datasets are just stored as output by the DFT codes, as I mentioned way at the beginning when talk about the need for Magres, these files are not interoperable with other DFT codes. And so standardizing the data outputs in a Magres form is desirable, which is why we encourage depositing the data in the database. And to enforce this practice more strictly, or like encourage it rather than enforcing it, I think we want more interaction with the journals and the communities, and we need buy-in from both of them to agree the standard Magres usage process, and for journals, for example, to request Magres files at the time of uploading to make it a common practice, which will increase database storage as well. And moving on to the interoperability aspect of it, I did mention the Magres attempt to standardize the NMR calculation data representation. At the moment, we have data support from CASTUP and Quantum Espresso, and there are still 20 plus DFT codes that need to include support for outputting the calculated parameters in the Magres file format, which presents a challenge. One approach is for us to go to each of the individual DFT code developers and say that this is a Magres format and this is the source documentation for how you can develop a parser for it. Can you please include support for this in your code? Or the approach that we took was choosing the Nomad materials database, which is found in this URL. And Nomad is the material database that's run by FAIRMAT in Germany, who are building a FAIR data infrastructure for the chemical physics of solids. And FAIRMAT, in turn, are an integral part of NFDI, who are the National Research Data Infrastructure, who, like PSDI, are striving to establish best practices around scientific data in Europe. And we asked them to develop a Magres parser because inherently they already include support for every single or a wide range of DFT code parsers in their database. So including a Magres parser directly in their interface may mean that there is a bit of a backwards compatibility where you have access to a wealth of other NMR data composed by other DFT codes that can be extracted back in the Magres format. That feature is not developed yet, but that is a lot of potential for that to happen. But other than that, I think the downside is that Nomad developers are still in charge of developing the Magres parser for us. They are quite interactive and helpful team. But it also means that CCP-NC who developed the Magres format are not in charge of the Magres parser for the format. And there may be issues like representation and different units being used to represent the data in a different database with the Magres parser, and we cannot take direct control of how we represent the data. And sometimes when we make requests for including features to the Magres parser, it may not be an immediate development requirement for the Nomad developers, and that may take a backseat in their priority, and hence we don't have the complete control of it. So that is one downside of it. And in terms of interoperability with other materials databases, we have attempted to use Optimate, but as you saw from the stack that I presented earlier, we lack the API translation layer that needs to mediate the conversation between Optimate requests and the Magres backend, which is lacking at the moment. I think there were efforts in the past, before my time, to make this happen, but this needed a much more dedicated development effort to match the Optimate's schema structure, which is more flat schema style, and Magres backend, which follows a much more nested data format. And the development effort for this was not available in the past, but it's definitely a highly desirable feature to have. And the final aspect of FAIR in the current version of the database is to use the reusability. I used the metadata problem. I showed the metadata blocks problem with the legacy quantum espresso codes. It's rectified now, but it means that there are legacy codes which were computed by quantum espresso and uploaded to the database that are still not sufficiently representative of the metadata, and hence there is still missing pieces of information for reusability. And in terms of data provenance, we don't really establish, like, because of the advantage of the Magres being lightweight, we also lack the additional information, like was there geometry optimization performed on the crystal structure before this DFT calculation was performed, or the crystal structure that's mentioned in the Magres file. How was this crystal structure determined? Was it experimentally determined, or was it determined by another computation? Is this structure compatible with an experiment that you are trying to compare this simulation data against? Since we are missing this data provenance, thus something that's pulling us back in terms of reusability because of the inherent design of our database schema. And because of all the mentioned issues in terms of FAIR that I discussed, and also the front end, there is the additional requirement that there needs to be continued support and maintenance for making the technology future-proof. When you develop the technology, you need to future-proof it and make it easily maintainable. And as I mentioned, which happened in our project, software developers tend to move projects and leave organizations sometimes, which leads to sometimes there being insufficient documentation being left, or due to improper maintenance of the technology over time, it can stagnate back, and it may lose its functionality, eventually usability. And all these mentioned challenges require us to redesign a new technology stack, for which we have gone through quite an involved thought process, and we want to implement a redeveloped version 2 of the Magres database. And in terms of deciding how the version 2 direction is, we have been actively engaged with PSDI's working groups in reviewing the CCP-NC community needs and thinking about making the best use of PSDI deliverables through this Pathfinder project. And given the number of requirements that we have listed, it would be impractical to rebuild the whole technology stack from scratch. It would be reinventing the wheel. It would be smart to look for someone who has maybe already a custom infrastructure built and think about how we can adapt it to our needs. And through our continued interaction with the PSDI's technology working group, we realized that Nomad database also makes available a service called Nomad Oasis for developers like us who can inherit most of the stacks that are available in the Nomad central version, or you can also choose particular functionalities and features of the interface that you want to use and build your own custom stack and plugins around it to adapt it to your community's needs. And we have had a first good in-depth discussion with Nomad developers about the feasibility of using their stack for building our technology. And as one of the first steps towards using this and still establishing a cost and benefit analysis to decide that this is the direction that we want to definitely go along, we have I have done a detailed metadata mapping to address any schema incompatibility or data migration that we may face when migrating our data to a new infrastructure. And also thinking about, since Nomad comes with out-of-the-box Optimate compliance and a higher degree of fair compliance, this helps us reach our goals faster. And currently, we are also in the stage of getting a deployment of a Nomad Oasis and testing what works and what doesn't work for us, and what are the things that may need custom redevelopment on our end, and how flexible Nomad will be for this. And development of this detailed metadata mapping, which is a bit too involved to show you in this presentation, has led us to a very useful and productive hackathon session that we recently had with the technology working group and the metadata working group together. And they have been helping us identify how to expose CCP-NC data for discovery through Optimate usage, and also via the PSDI portal that's in development. And they have been guiding us to think ahead about using standard chemical identifiers that I mentioned, and revisiting and revising DCAT and indexing after upgrading to a new database technology. And as PSDI's partners, we hope to also benefit from the expertise and guidance of CCDC, who have partnered with PSDI, but they are also part of the CCP-NC steering group. So we get best of both sides from them. And their guidance towards adopting the best practices in using chemical identifiers and developing advanced structure searching, and using these two, their guidance on chemical identification and advanced structure searching will be most beneficial for us, together with the guidance from PSDI working groups. So if we go to Nomad, what are the considerations on our end? I'm almost finishing the presentation now. This is coming to an end. Moving to our vision for a version 2 of the database, thinking what are the things that we gain by directly adopting the Nomad's infrastructure and technology. First is the Optimate compatibility that we get out of the box. So we don't have to think about mapping our metadata independently through a translation layer to Optimate, and also making it suitable for compliance with the Nomad's backend. So we can just think about one, and Nomad out of the box comes with Optimate compatibility. And Nomad's metadata schema has been developed over time with multiple past collaborations, and the fair compliance has been built in a flexible way. And they still have flexibility to accommodate the metadata requirements of a dedicated research community such as CCP-NC, where we can get the best practice guidance from PSDI, incorporate them, and still make this part of the Nomad's data schema. There is flexibility for that to happen. That's an advantage for us. And as I mentioned before, developing a future-proof technology stack with continued maintenance requires dedicated support backed by continued funding. So, but Nomad have currently good financial backing for the foreseeable future, and a big dedicated development team to support their infrastructure so that we can benefit from their long-term support. And there is definitely room. They provide a workflow framework where a user has the option to upload multiple additional files associated with their simulations to establish data provenance for a more efficient reusability feature. And thinking about what CCP-NC side of things will be, what will CCP-NC be doing to contribute development here, and what are we giving back to Nomad? in the end. So CCP-NC first has the freedom to adapt Nomad's front-end/dashboard into our custom front-end and to provide a tailored experience for the CCP-NC community users, and also to develop our own plugins to localize it for the community usage. And a desirable user experience feature, as I mentioned before, is to integrate more data visualization tools on our front end so that people can make best use of the data for data analysis, comparison with experiments to make more informed decisions in search for materials in their research. So Nomad has an additional feature where they provide the option for developing dedicated apps, which are like plugins and customized dashboards that you can develop for your community, which is quite handy that we can make use of. And since we will be handling the development on our end of our version of Nomad Oasis, like the CCP-NC Nomad Oasis, we have more control of how we develop the Magres parser to suit it to our community's needs to best represent the data. And we can feed it upstream to the Nomad community as well so that they can standardize best practice with Magres and standardize it for the rest of their community. And there are also, lastly, special features to think about, as I mentioned, the advanced crystal structure-based searching and adopting standard chemical identifiers that I had mentioned. These features are not available as part of Nomad infrastructure. These are developments that we will still be undertaking on the CCP-NC side with guidance from PSDI and partners. And once again, this may be quite useful features that the rest of Nomad community can make use of as well if we pass these features back for them to incorporate within their framework. And in terms of delivering the current requirements and the vision for achieving the goals that I mentioned is for the database version 1, the database version 1 still needs to exist while database 2 is in development for continued use by our community, and they have requested multiple features that still needs to be provided to them until the complete database version 2 is deliverable. And as I showed in the demo, the Boolean search is already been delivered, and bulk downloads is currently in development. And the upload experience, I said, could be more user-friendly. That's to be improved. And there has been a request to incorporate a bigger machine learning data set into our database as well, for which we have acquired a machine learning data set, but there needs to be some initial bit of optimization and appropriate data tagging to identify that these are machine training suitable data sets, and then uploading them. There need to be some initial adjustments that need to be done on our part, but this is also in progress currently. And I think the version 1 deliverables can be confidently become available by March 2025. Thinking about version 2, there needs to be a lot of effort that needs to go into making the version 2 of the database. Since we are making it once and we are making it as a sustainable, long-term, maintainable product, we want to think about incorporating the best metadata and chemical identification practices, which are fed into by PSDI guidance, and the improved technology stack with API layers. The disclaimer here is that just having API doesn't automatically make a technology stack better. It needs to serve the purpose. But what I mean is identifying the best API that are needed for achieving the functionalities that we want to achieve better and for fair compliance in our database, and incorporating them, and incorporation of additional advanced data processing tools for better data analysis by our community. And by autumn 2025, we aim to make the product completely ready for discovery via the PSDI portal as well, by working closely with the metadata and the technology working groups of PSDI. And thank you for your attention. And I think I already have a question. And is there any gatekeeping for upload of data? By gatekeeping, I assume you mentioned the ORCID, like authentication. I think ORCID authentication is sufficient gatekeeping that we do, because ORCID neatly links to the researcher's public profiles and public research profiles, and lets us authenticate the users and store their information in the backend along with the records. So that is the gatekeeping that we do for uploading.
Thank you very much, Satya, for a really interesting presentation. Yeah, that was really great to see the overview of all of the work that's been going on, some of the considerations that you've had to make. Obviously, a lot of this things around some of the issues, obviously, well, working with some of the standards and sort of going towards that. So put up a link for most of our socials, but I just want to say a massive thank you to Satya for coming along and presenting today, and to all of you for attending. And I hope you have a lovely rest of your day.